I must say I love coming back to the Rock. I remember from my days as a graduate student in the 1970s being out at Millbrook with Peter Marler and Fernando Motobaum, looking at the similarities between language acquisition in babies and birds and the acquisition of birdsong. And of course, more recent visits have brought me into closer contact with Bruce McCune and Mary Beth Hatton, Corey Bargman, and Jim Hudspeth. Neurosciences here at Rockefeller, it's really, really an incredibly rich group of people. Well, I'm here tonight to talk to you about the baby brain and how the foundations of learning, how our understanding of the foundations of learning has completely been revised by the kind of data, both behavioral and brain, that we've acquired over the past 10 years. Particularly the last 5 years, our understanding of the child's brain has grown immeasurably. So I've just come from Stockholm and Madrid, flying in just on Sunday night. And in both countries, the governments are asking, what do we do with the children? So just as many of you are parents and grandparents, or you're very interested in children and their minds and brains and how incredibly they learn, it's a resource none of us want to waste. And I'm struck by the fact that all over the world, governments and normal, regular people are trying to decide, what do we do with our children? So in Stockholm, the Crown Princess has questions about her daughter, the future queen. How do I raise this child? And how do I teach her multiple languages and help her to thrive without the pressure that comes with the job? And in Madrid, the Madrid system of the Greater Madrid Educational Ministry has 6 million children in its charge. And from 0 to 3, they have 55% of the children under the age of 3, from 4 months to 3 years, enrolled in their preschools. And at 3, it's mandatory. So 100% of the 3-year-olds are in the preschools. And I visited many of them. And their goals are, of course, to bring up bilingual citizens who their lives are enriched, they're literate, they're good in math and science. They want their girls as well as their boys to thrive in STEM disciplines. So we're all asking the same questions. Their question to me is, how do I design these schools? They would like me to help them design the schools. So tonight, what I'd like to do is I think about taking on that assignment. I'm not certain I'll take on that assignment. But as I think about what do we know about the minds and brains of children, what can we tell society? What can we tell a group of people like yourselves who are interested as parents in science? What is the set of examples that we can bring to bear on the design of classrooms and interactive experiences that will help all of our children reach their potential? So what's fun about being in this field at this time is that all of us have the intuitive understanding that children are genius learners. They have amazing capacities to absorb information. What we didn't understand, I think, until more recently, is that brains have to be built. They come ready to learn, but they really do need to be constructed. And so this sense that there's a responsibility on us as parents and as society more globally to help the children come along is something that's really interesting to pursue. Now that we have brain science as a capability for the youngest citizens of our world, I will tell you tonight about the newest experiments in the laboratory, my laboratory at iLabs in Seattle, in which we take young babies and put them in completely safe rocket science technology called MEG, magnetoencephalography. MEG is perfectly safe, perfectly non-invasive, and allows us to get movies of the brain in action. You'll be surprised to see what those new movies are telling us about the baby brain. At the same time that we're interested in brain function, we've developed at iLabs new measures of brain structure. We can now do voxel-based morphometry with the baby brain, meaning taking all of the areas, 1,000 areas in the brain, and measure the white matter development in a particular area and see which areas predict skills like language later, a year or two later. And we can see tractography is allowing us to see the enormously beautiful connections that are allowing areas of the brain to talk to one another. So studies of brain structure and function are leading us to both rocket science about the children's mind, but also a new era in which the science can actually inform how it is that children learn and helping families who otherwise don't know what it is that would be best for children. So in studying children's learning, one of the phenomena that become very fascinating for scientists, biologists as a group, is the idea that in some domains we know there are critical or sensitive periods for learning. So if you look at this curve, find your age at the bottom, and then look at your skill level on the vertical dimension, you can see that there really are three different levels of learning capacity that are not equivalent over the age span. Children are best at learning a second language, and that's what we're plotting here, the ability to learn a second language from 0 to 7. And the second best time to learn is between, right after 7, from about 8 to puberty. And after puberty, something changes dramatically. The same machinery isn't used. It isn't as though you can't learn a second language after puberty. You won't learn it in the same way, however. You won't use the same brain machinery, is our hypothesis. And you won't learn it with the same facility, particularly the nuances of grammar and the nuances of pronunciation. So the reason we want to understand what children are doing is that, they're putting some magic to work in that first 7 years and in the early period that I can't put to work anymore, nor can most of you. So the question is, what is that magic that they're putting to work? What is it that changes over age in our ability to learn a second language? It's also important to study the early period because that is when autism, specific language impairment, Fragile X, and all, dyslexia, all of the disorders that have to do with language take root in that early period. So our hope is that understanding the magic that kids are putting to work in the early period will help all of us someday keep our minds alive to learn second languages, also help diagnose, develop early biomarkers of children with developmental disabilities at a time when the brain is very plastic, so that novel interventions based on what we know about how children learn can be put to work. So we've been studying the earliest sensitive period with regard to language, and we've learned a lot about how infants learn, not only for language, but more generally. So the earliest period of learning for language is learning about the sounds. All languages have consonants and vowels, about 44 per language, and they differ across all languages. Japanese, English, and French don't use the same consonants and vowels. Somehow, to acquire words by the age of 1 year, babies have to work out the sounds. Which sounds make a difference between words in the particular language that they're trying to learn? So we made a discovery depicted on the next slide, not only by studying children in these two countries, Seattle and Tokyo, but we've actually, members of my laboratory have been to 9 different countries, and we established very globally, along with other laboratories, that babies begin life with regard to hearing the differences between sounds as citizens of the world. So if you look at this graph, we're measuring babies at 6 to 8 months, and then again at 10 to 12 months. And what we see when infants are being tested either with a behavioral or brain measure, if they can hear the difference between 2 syllables, ra and la. Very important to English, not important at all to Japanese. So at 6 to 8 months, all the babies in both countries are doing exactly the same with regard to their ability to hear a change from ra, ra, ra to la, la, la. In behavioral measures, they turn their heads. In brain measures, we're taking an event-related potential, a sensor on the scalp that measures the brain's reaction to a change. So at 6 to 8 months, they're at about 65% correct, and not perfect, but well above chance. But 2 months later, something pretty amazing happens. Between 8 and 10 months, the American kids get a lot better, and the Japanese kids get a lot worse. What's interesting is both groups of babies are doing exactly what they need to do to acquire their native language. Japanese babies should be ignoring the difference between R and L to acquire Japanese words. And American kids should be honing in on that distinction in order to learn words like read and lead and all the other words in English that are differentiated by R and L. So what we have here is a sensitive period for sound learning right here between 8 and 10 months. Now, who would have known that other than through the scientific investigations? So that's a very incredible period with regard to children mapping which sounds are important to the language. And we have learned in studies that are not published yet, but in a dissertation finished just this past year, we learned that this ability to make that change, to acquire a skill in native language sounds and decrease your skill in non-native language sounds, that learning predicts reading language at 2 years, language at 3 years, and reading readiness at the age of 5. Now, that's pretty amazing to take a measure early in development and see its continuity 5 years later. So, of course, as a scientist, we ask, what are the children doing? How do these young babies learn between 8 and 10 months? And the answer is they're using 2 very different strategies. One of them is statistical, computational, and the second one is social. And so I want to describe what these 2 are like. So with regard to statistical learning means that babies are sensitive to the frequency of events in their world. They're also sensitive to transitional probabilities between events, like between 2 syllables. 2 syllables that always hang together are interpreted by young baby minds as a word, even though they have no idea what the word means. 2 syllables that come together, like bay and bee, become baby, a unit, before they even know what baby means. They understand that's a unit, that's a word. And their understanding of the sounds of the language is coming partly from this distributional frequency understanding. They are taking statistics as they listen to us talk. So I want to illustrate how that works. I'm going to have you listen to an American mother speaking Motherese, and then a Japanese woman speaking Motherese. And Motherese, I'll give you an illustration later, but Motherese is sort of milk for the brain. Babies love it. They'll choose it if you give them a choice. And it is actually very, very good for their acquisition of language. But first, let's listen to these 2 women, and then I'll tell you what's going on in the baby mind as babies listen to us talk.
I love your big blue eyes. So pretty and nice.
うわー、大きな茶色いお目目。そして綺麗な黒い髪。
It's interesting, isn't it? It makes you smile. It's a very happy sounding signal with its raised pitch and slowed down sounds and very extensive time. It's like you're dragging the sounds out so the baby brain can really map them. But what's happening in the baby mind as these signals come by, infants are very sensitive to the distributional changes in frequency. So when they listen to American English, there's lots and lots of R's and L's. Very few Japanese R, which is a signal between American R and L. Whereas when you listen to Japanese, there are many, many. There's a unimodal distribution, a lot of Japanese R, but no American English R's and L's. In 2 minutes in the laboratory, you can change babies into Japanese-like listeners or American-like listeners by changing the distributional frequency of the sounds. Now that's simply astounding, that infants are listening to us talk and their brains are mapping the frequency of the sounds before they understand a single word. This works in vision as well. So visual signals operate in the same way. The frequency of visual signals change what babies perceive. And in movies and stationary sounds in music, there's a lot of different signals that have been tested. Babies learn statistically because they're sensitive to the probability statistics of information in the world. So that's one way that they're learning, and it reminds us that if babies are taking statistics, they obviously have to have some signal to work on, right? They have to have talkers who are speaking to them. And so we stop here to say, remember, Hart and Risley in 1995 demonstrated by recordings made in the home that children coming from different families, professional families, working class families, and welfare families, hear a lot different numbers of words. So how does the brain do its work if the child is growing up in a welfare family where the number of words per hour is relatively small compared to kids in professional families? So when you do the math, the outcome of the study was that by the age of 4, there's a 30 million word gap. So the statistics that infants are taking do depend on us talking to the kids. So the second piece, though, is different from computational learning. It's social in nature. Part of the social interest that children have in speech is this signal called motherese that you just heard a piece of. Motherese is universal across the languages of the world. No matter what culture you're recording in, if you record a mother in adult-directed speech at the top and then in infant-directed speech at the bottom, you get this huge contrast in the pitch of her voice. And the top record, she says, aha, I had a little bit, and the doctor gave me Bendectin for it. So she sounds like she's got a typical pitch contour like I'm using now. It's not dull, but it's not as exciting as what you hear if I happen to have a 2-monther in my lap, and I turned to that 2-monther and I said, can you say, ah? Say, ah. Hey, you. Say, hi. Hi. I can't, it's too. No baby here. 700 hertz. So these extreme changes in pitch are very attractive to infants, no matter what language it is, no matter what country you're recording in. If you give babies a choice, they will choose to listen to a person, mother, father, grandparent, or older sibling, speaking this motherese or parentese signal, as opposed to adult-directed speech. And we now believe that these kinds of signals are very, very good for babies. Here's our most recent study on parentese, and I wasn't going to show too many graphics tonight, but this is really easy to grab onto. On the left, we're looking, each dot is a family, recorded at home. The babies are wearing a little Lena recorder. It weighs 1 ounce. They wear it 24/7 for a number of days. And we're just looking at what are the kids listening to? How much time is the TV on, the radio? Who are they listening to? What is the signal they're hearing? And we're comparing parentese speech and adult-directed speech and its impact on babbling, the kids talking back, and later language 2 years later. Now the graphs for babbling and 2 years later look the same, so I'm just showing you babbling. This is a no-brainer. As the increase in parentese, the percentage of time kids are hearing parentese increases, their babbling increases. Whereas adult-directed speech, pretty flat. It helps, appears to help, to have a household in which parentese is being spoken by the people who are interacting with the child. The second one was less predicted by us, and it demonstrates the role of social context. We were comparing whether kids are being talked to one-on-one or whether there's a group of people talking and sometimes addressing the baby. The answer in this case is that one-on-one interaction, again, we see it on the left. The more one-on-one interaction, the prevalence of one-on-one interaction in the home is very, very good for it is strongly associated with language both at the concurrent babbling stage and 2 years later. Whereas group interaction is less, it's flat. It's not a decrease, but it's flat. So we have these social signals that are coming from people that babies are very interested in, and particularly motherese appears to be associated with good outcomes. Another very important finding is that the infants don't learn from television. Now, maybe you're not surprised by that, but the world was pretty shocked and business was pretty shocked when we illustrated a few years ago in experiments that I'll tell you about that infants, while they are fascinated to look at a television set, are learning, at least in the very early period. They're not learning from it. So here's the setup for the experiment. Just as we had been in Tokyo and in Seattle looking at English sound perception, we've been in Taipei and Seattle again, measuring the perception of Mandarin Chinese. So sounds like shi, which I can't pronounce as distinct and I can't hear it as different, but my graduate students and postdocs tell me all the time, Dr. Kuhl, if you were trying a little bit harder, you'd hear the difference between she and she. It's hopeless for me because I didn't hear it during my critical period. But the kids in Taipei and in Seattle are behaving again as we'd expect. 6 to 8 months, they're perfectly and equally good at this Chinese Mandarin distinction. 2 months later, the Taiwanese babies are getting very good and the American babies are getting very bad. And they're both doing what they should be doing to acquire the languages that they're going to acquire. But here's what we did in this experiment. We did an intervention, 12 sessions between the age of 9 and 10.5 months during that sensitive period. We brought babies in who had never been exposed to a foreign language. And for 12 sessions, they played naturally on the floor, listening to Mandarin Chinese or, in later experiments, Spanish. So this was an intervention taking place right at the sensitive period, and we wanted to know, what does it do to their brains? Can they take statistics on a new language for the first time at 9 months, or do they have to build up statistical distributions over a long period? Well, here's what the sessions looked like as the babies played on the floor with their Mandarin tutors.
Jasper， 早安 Finn， 嗨，我们要来讲一个故事哦。今天要讲的故事是《小熊七七探险记》，来看看发生了什么事情哦。小熊七七在这里，一个绿色的圈圈，绿色的圈圈，绿色的圈圈，再转一下，转一圈，嘿，一圈，再一次哦。转一二三。
Okay, how's your Mandarin coming along? All right, so the question is, did the babies learn? What effect did this 12-session experience have on their brains? So we had to run a control group, of course. You couldn't just assume that coming into the laboratory by itself wasn't having an effect. So we had a group of graduate students who were American English speakers, and they played on the floor, same dosage, same time table, but were speaking English. So first of all, what does the exposure to English do to their Mandarin perception? Nothing, which is good, of course. A scientist doesn't want the control group to do well. The control group has to look as though everything stayed the same, which of course it did. But look what happened to the babies exposed for 12 sessions to Mandarin. They were statistically equivalent to the babies in Taiwan who had been listening to the language for 10 months. What's the lesson here? Give the brain what it's interested in at the particular time in development at a sensitive period, and it is like magic. No matter what they listen to at this period in time, whether it's English or Mandarin or Spanish we've shown, they learn. And not only the phonemes of the language, but the word forms that they hear. Not saying that they learn the meanings of words, but if you give them, as we did in Spanish experiments, 10 words that they heard frequently versus 10 words that they never heard at all, their brains were responding after those 12 sessions to the word forms of the sounds that they had heard. So this is a magic interval for babies and their ability to acquire information about the sounds that are used by speakers of the language. So of course we wanted to know, babies in these experiments were very, very excited. They'd watch the door in the waiting room to see when their tutors were walking in because they loved these experiences. So we wanted to know, what happens if you take the human being out of the equation? What if you just present from a beautiful DVD and everything else is the same? Again, same dosage, same number of sessions, everything is the same. We ran another experiment, 2 groups, 32 babies watched a television set. 32 babies had only the sound and watched a teddy bear on the screen. So is it sufficient to have infants, if it's statistical learning only, then running the information across the basilar membrane ought to be enough. So what happens? What did these kinds of experiences do to the baby brain? First of all, the audio alone conditions. So they're just hearing it and looking at a teddy bear, no learning whatsoever. What about the TV group? No learning whatsoever. We were surprised by these results because babies looked at the television with great interest. They would crawl up to it, they would touch it. We had babies kiss the television set. So they were looking as though they were learning. But both the brain and behavioral measures after the 12 sessions showed no learning whatsoever. They're equivalent to the kids who had been exposed only in the control group to English. So there's something about the social experience. What is it about the social experience that opens up that gate? We're calling it a social gating hypothesis. We're saying the presence of another human being changes the brain's response to particular kinds of learning situations, in this case, language. The baby brain needs a social experience to learn language. We now think from other experiments that aren't published yet, too early to talk about them, there's a motivational component. Something happens to energize and excite the brain of the baby in a social circumstance. And second, there's information provided in a social context. Babies follow the eyes of the tutor. When the tutor picks up an object and names it in Mandarin or Spanish, the babies follow the eyes of the tutor. Eye gaze following, a social skill that we all have and use intuitively all day long, every day, comes online at about that time. So there's something very special about the social brain and language learning. Perhaps many kinds of learning in that early period are socially dependent. The bilingual baby brain, let me say a little bit about that before we get to the brain data. We've been following a group of children in San Antonio where kids in that area, 55 families have been enrolled, are listening to Spanish and English about equally. So often a grandparent is speaking Spanish and the mother and father are speaking English. We're both studying the parents and their knowledge of what they should be doing to help their children, as well as the children themselves, taking brain measures not with a big MEG machine, but with event-related potential caps. And what we're showing is that these bilingual kids, their vocabulary growth is totally equal or better than monolingual kids. As long as that language input is coming in both languages equally, these kids are thriving in both Spanish and English. We're also showing that the bilingual experience, just the chance of listening to two different codes, seems to keep the learning period open longer. Now, if we can demonstrate this more solidly, we have initial evidence that's published 2011 that just getting bilingual experience makes your learning period more flexible. If we can show this definitively, it's very, very important for the notion of critical periods, because the notion that a sensitive or critical period opens at a particular time and closes sharply at a particular time does exist out there. This would say the environmental experience can modify the duration of that critical period. We're also demonstrating that kids are flexible. The bilingual children are flexible in other ways. We have a set of experiments that illustrate that children, we know that bilinguals at all ages have more flexible brains, meaning not that they're smarter in general, but that they're very, very clever when it comes to inventing a new solution to a problem. Their executive function skills are highly trained and exceed those of monolinguals at every age that we can test. So we wanted to know whether babies, really young, these are 11-monthers who'd been bilingually raised or monolingually raised, had the same or different cognitive flexibility skills. So the test is a plexiglass box where we hide a toy. The baby's job is to get the toy out of the box. Of course, they love doing this. But then we turn the tables on them. We turn the box around, so the one door that's open to the box is now on the other side. The question is, can they figure it out? Can they go in the opposite door? Here's our monolingual child solving the problem. So there's a little toy, it makes a noise, gets hidden in the side that's open, and so she pushes on the box and looks at the box and tries to figure out how to get it, and then finally figures out, yeah, you pull it out of that open plexiglass door, and that's really fun. Now, we turn the box around and see what does she do when she has to invent a new solution. So she's done this a few times through the door that was open on the other side. Now, so she goes back to the old way of doing it. It's always worked before, and yet now it's not the way to get the toy out of the box. She can't figure it out. All right, now watch a bilingual child of the same age do this task. Okay, first on one side. All right, same kind of pushing on the box. And then figuring out, yeah, that's how you get it out. Okay, this is great fun. Got to have that toy. All right, so now we're going to do the same thing. Take that box, turn it around. They can see that it's going in. All right, so what does she do? She's going to try the old way, but it doesn't take her a second. And she pulls it out. She works really hard to get that toy out of the box. Okay, so the general finding is that the bilingual kids are a lot, statistically significantly better at 11 months than the monolingual kids at solving this task, both on their percentage of accuracy at solving it and if you take a speed measure at the latency to solve it. So bilingualism is good for the baby brain. That toggling back and forth between the two languages gives the brain a kind of exercise in the prefrontal cortex that seems to be good for these kinds of problem-solving tasks. So with that as your behavioral background, you can imagine why about 5 years ago we intensely at iLabs decided that we needed a toolbox for the developing brain. So we have about 10 of us from physics, biophysics, the medical schools, departments of neuroscience and radiology, neuroscience, psychology, speech and hearing, linguists. We're all actively engaged in the task of analyzing the baby brain. So we now have measures. We have done head models of the baby brain. We now know with 150 12-monthers and about 83 6-monthers what the brain looks like of a baby. Baby brains are not just shrunken version of adult brains, but different in their shape and size. With these kinds of measures, we've demonstrated that when you do voxel-based morphometry, meaning you take the 1,000 areas of the brain at one age, say at 6 months, and then you look at which of the areas of the brain, white matter and gray matter concentrations, predict language skills later. We've learned that the hippocampus and the cerebellum are the two areas that at 7 months predict language skills a year later. Not surprising when you think about it, because memory, babies are remembering the hippocampus and its memory skills being activated by listening to us talk and storing that information. And then the cerebellum, the motor planning area that allows infants to talk back. So these experiments extend beyond the areas of the brain to the connectivity. So with tractography measures, diffusion, tensor imaging, we're able to see fiber tracks in this 9-monther's brain. You're seeing here now everything connected through the corpus callosum. Corpus callosum is the biggest superhighway in the brain connecting left hemisphere and right hemisphere. And so even in a 9-monther, the pink is the strongest fiber. You can see that the baby brain is well connected. By the age of 5, when we send our kids to school, look at that brain. Very pink, lots of connections going from right hemisphere to the left hemisphere through the corpus callosum, and just for comparison, the adult brain. Of course, more connected and more stronger pathways. But the idea that we can now see in a 9-monther the fiber tracks, we can measure the myelin, the degree to which the myelin sheathing allows fast communication throughout the brain. We're now doing studies relating the child's environment to that tractography. And we can already see that in babies and, of course, in adults, the bilingual brain and the monolingual brain are wired totally differently. The monolingual brain has a higher FA value, meaning many fiber tracks all going in the same direction. The bilingual brain, as you might predict, has more exits off the highway. Radial diffusivity is significantly higher in many places in the brain. So that experience of 2 languages changes the basic wiring diagram of the brain. So now we move from static pictures of the brain to our newest magnetoencephalography. Now, of course, this looks like a hairdryer from Mars, doesn't it? $2.5 million machine, but it's the only way that you can measure function in a baby brain in a completely noiseless, completely safe environment. We were the first in the world to measure a 6-monther, a baby, awake in an MEG machine. So you're seeing a 6-monther who is listening through insert earphones to the words and sounds of different languages, while we measure through 306 squids located in that hairdryer. Squid devices, superconducting quantum interference devices, are picking up the magnetic field changes that are directly coming from changes in neuronal firing. So this baby's totally comfortable. They can move because we've got GPS tracking for the head. So we always know where the brain areas are as the baby moves in the experiment. So it's a technical tour de force to be able to do this kind of thing. What are we seeing? Well, in the next movies, I'm going to show you our first result published just this spring in PNAS, Proceedings of the National Academy of Sciences, demonstrating what happens as a 12-monther, a monolingual child, hears a control signal in a syllable in English, and then we play Spanish. And we want to know what areas of the brain are active. We, of course, predicted there'd be a lot of activity in the auditory system where the baby is hearing the sound. But what about other areas of the brain? We were particularly interested in the areas in which babies plan their own motor movements, the Broca's area and the cerebellum. So let's see what we see. So here's our 12-monther monolingual child, the areas of the brain that we're coding, 150 coded, we're actually measuring 1,000. But in this experiment, we're paying attention to 2 auditory areas where signals are being registered, and Broca's where action, planning is going on, and the arcuate that connects them. Okay, so here's what happens. The bubbles that you see are MEG volumetric data. This is the firing in those areas of the brain. The red curve is auditory, the blue curve is motor, but if you can just watch the bubbles, you'll see what's happening. Lots of activity for the standard sound, common to Spanish and English, then the English test sound, both auditory and this Broca's area is active. For Spanish, again, a little bit lower in this 12-monther, the auditory response to Spanish, but a bigger response in the motor area. We're interpreting the finding to indicate that as babies hear us talk, they're not only listening and beginning to master the auditory signal, which accounts for the increase at 12 months, the standard to the English test, they're really heightened responses to native language sounds. But their motor areas, we believe, are rehearsing. What is it going to take for me to respond? I want to join this conversation. The baby brain is so socially driven that they want to do what we're doing. They want to move their mouths in ways that will allow them to talk back. And we see that as early as 6 months, well before children will produce their first word at 12 months. That motor brain, both Broca's and the cerebellum, are active. And by 12 months, why is the motor area more active for Spanish? Because they don't know the motor plan for Spanish. At 6 months, we see equal responses in motor areas and auditory areas to the native and non-native language. But by 12 months, their brains have become specialized. They hear a French vowel, and their motor brains are going, "What's that? I don't know how to talk back to that sound at 12 months if I never heard it." What's exciting about this is the notion that we wouldn't have had a clue that the motor areas of the brain are active as children hear us speak without doing these kinds of experiments. You have to get under the hood. You have to see what's happening in the baby brain to understand how it is that they're coming along, and by 12 months, this fairly quiet baby will start talking back to you, will start talking in a way that surprises you. Within 6 months or a year, a vocabulary of 50 to 100 words, and by 3 years of age, they can talk your leg off. And the answer to part of that problem is that they've been working on the motor plans to join the conversation since the early period. So the last thing I want to tell you about is how sensitive we think these brain measures are going to be to developmental disabilities. What you see on this slide is a publication from 2013 showing that if you take measures of the brain's response to words at 2 years of age in children with autism spectrum disorder diagnoses at the age of 2, we predict outcomes at age 6 better than any known measure. So, and not only outcomes with regard to language. You'd think if you'd measured with a word, you might be showing outcomes only for language. The ability to learn words predicts their cognitive abilities, their adaptive behaviors, and their receptive language skills at the age of 6. We also measured at 4. They're equally good at 4. They get even a little better, the predictive value, at 6. I think what this means is that if a child's brain can learn socially, meaning can take statistics, can learn in a social setting, then that predicts the ability to learn quite generally, not only language, but other things about the world, about objects, about behavior, about problem solving. So we think that at some point in the next 5 years, we will have measures. This is with children diagnosed at 2. 2 is too late as far as I'm concerned. I would like to be able to, or it's not early enough, put it that way. It's not early enough. We'd like to have biomarkers at the age of 3 months, at the age of 6 months. This is when the brain's window of opportunity opens for language and other skills. We'd love to be able to have biomarkers that indicate risk for various disorders of development, so that when the brain is plastic, we could bring about a much more clever set of interventions because we understand how it works. One of the experiments that we have underway is face-to-face social learning. Well, obviously, if you've understood what I've said tonight, I think the social experience, being face-to-face with another human being, is critical for infants. And we're trying to understand how is it that brains are so fascinated by the face-to-face interaction. I think it's true of ourselves too. We're starting with the kids. The baby's in the MEG machine. The mom has an EEG cap on that's co-registered. So the machinery is now looking at both brains and looking at the interaction between them. And preliminary work that we've done suggests that brain rhythms come into alignment as babies and their mothers are interacting in a very, very wonderful exchange. You'll see the brain rhythms come into rhythm, into synchrony. What, of course, would be interesting when you think about all of the work on children who are abused or neglected, foster care kids, kids who have experiencing toxic stress. The notion is that we might be able to see some of that disorder in a relationship taking place very, very early by understanding what is the effect on the brain of a baby of very, very, very unpleasant, toxic stress kind of interactions and environments. Finally, we think the science of learning is just starting. These data are very exciting, but as we wrote in 2009 in Science, colleagues and myself, all involved in science of learning centers, there's a new collaborative set of studies going on that brings psychologists together with neuroscientists, that bring people in education and those in machine learning, because machines are being mapped to learn. They may learn similarly or differently from humans. We're learning from machines and they're learning from us. That is going to be an important mix in the collaborative kind of science that's going on. It makes it very exciting to imagine us being able to design schools that are based on children's abilities at the time in development when experiences that their brains are ready for are presented in schools in a way that makes them able to learn better than current classrooms are oftentimes allowing them to learn. So thank you for listening, and obviously this kind of science takes many, many collaborators that are very different with regard to their basic training and with regard to their country's origins. And of course, it takes a lot of support, and I want to say thank you to all of the people who are doing so much to help my laboratory make and my students make their work progress. So thanks very much for listening. Thank you.
Fabulous.
So, yeah.
Well, thank you, Dr. Kuhl, for just a marvelous presentation. We have time for some questions now.
Be interested in knowing what your research suggests our policy program should be towards education, pre-K, parenting. How does this translate into what we should be doing with our children?
Right. I think step number one is to pay attention to the science. I think that an educated audience like this has a lot of intuitions that are correct about children. But it's fairly amazing to me, and it would be amazing to you, to talk to the parents who think that talking to their children, for example, is not necessary. The children aren't talking back, and so it's not important. So one of the things I think we need to do is to get this information into the groundwater. We need to have people understand very generally that the power of parenting is the notion that if brains need to be built, and indeed they do, that the kind of things that we do in our everyday lives, talking to kids, interacting with kids socially, and spending time with them, challenging their young brains, is very, very important. Now, governments will get involved. The governments of many countries are trying to put their resources to work here, but the parents are the powerhouses. Parents care, every parent cares a great deal about their children's success and happiness. And I think this kind of information in front of parents is very empowering to them. In our bilingual studies in San Antonio, I didn't have time to mention that these mothers are in Head Start programs. These are mothers who are typically teenagers. Many times the fathers aren't around. And the woman pictured in the slide was 19, and this was her 4th child that she was holding. She knew nothing about her role in bringing up that baby brain. But as we showed her in plots how her baby's brain was responding to words, and then having her write down how many times she was reading and talking to the child, it was like wildfire, it took off. Parents get excited. It's empowering to think that it's your ability to bring that child up, not fancy toys and computers as much as it is you.
Thanks so much for your comments and all the good work that you do. 2 quick questions. The first is, have you looked at biomarkers as it relates to ADD? And secondarily, could you give us a little sense of the scope of the research you're doing in terms of dollars, and what projects aren't funded that you might want to fund? I figured
that's a good question. So the scope of the work is to, at the Institute, we're trying to master the first 5 years. We're interested in human learning, so the kinds of learning that only humans do: language, cognition, social interaction, problem solving, mathematics. So those are the skill sets that we're looking at, and we're attempting to understand both behaviorally and from the standpoint of the brain, what are the measures that you can see early on predict how this child is moving through that growth curve. And the surprise is that these markers are so sensitive so early. So when a 6-monther shows that their ability to hear the difference between ah and e predicts language and reading readiness out to the age of 5, that's pretty amazing. And maybe more amazing still, we're associating that with the environment, meaning we don't think that. We've got evidence to suggest that it's not just your hearing capability or something, the machinery you're coming with, but your ability to learn given the environment. And we think environment's what's pushing that around. So the biomarker work is very new, very exploratory, but very exciting given the results that we already have. So we're interested in anybody interested in the first 5 years, both typical development and the development of biomarkers, and think that understanding the principles of how we learn in our first 5 years will set the stage for understanding adolescence and set the stage for understanding aging. That's a broad claim, but we have evidence from some of the markers in development are the ones that allow us to measure how fast kids are moving, zooming forward, are exactly the ones that allow you to measure how rapid the decline is in old age. So that investment in the first 5 years is to us a measure of learning throughout the lifespan. And that's why we think it's such a good investment.
What a wonderful presentation. Thank you very much. I was very interested in what you said about television. You don't learn. But are there any negative, long-lasting effects on language development, on thinking, creativity, by watching too much television?
Right. Well, so we have, this isn't my study, but it was done by a group in Seattle. If you looked at the number of hours babies under the age of 16 months watched television every week, with every increasing hour of television per week, the children knew 5 less words. Okay? That's not a good impact, is it?
No.
And that's under the age of 16 months. So the message that we're getting from the science is not that television is always bad, but in the early period it is bad. It's replacing something that should be happening instead. You think about the awake hours of the baby. That time's precious, and that time needs to be in human interaction and exploring the world through the eyes of parents and others, so that you can, all of the things we're seeing in the brain, you're reacting to a baby is not only activating their sensory systems, but getting them ready to act back. We're creatures that want to not be couch potatoes and just take in information. We want to act on the world. The baby brain wants to act on the world right from the beginning. So putting them in front of a television set, we're doing MEG studies now, where we're exposing the babies to a new language live versus the television set. And we can see differences. We don't have enough kids to describe the whole panoply of differences, but the brain reacts differently. You're watching a flat screen as a baby, just like us, you kind of go into couch potato mode. You're not planning on interacting with that screen. You're just relaxing somehow. You're just turning off. But in live interaction, the brain's doing something totally different.
Can you talk about reading and its impact on the brain? I'd read somewhere that if you read, someone waltzes through the room, it actually activates that physical action, that desire to act. Can you talk about reading versus the talking to a child?
Right, exactly. So, reading takes explicit instruction. So while language in the right environment will simply happen, meaning the brain is set for oral language, reading takes instruction. And we think that it's not too far to say that reading begins in the crib, in that the kind of language that's being established in the brain, those circuitries, those architectures for oral language are setting the child up for a differentiation between sounds that differentiate words, that can be aligned with regard to the sounds you hear and the letters on the page and the words that they create. So instead of it being a kind of disjunctive step at age 4 or 5, we think it's a kind of continuous process. And that's why these early measures of learning and attention to the sound differences is making such a leap to predict phonemic awareness and reading at the age of 5. So we've got a study underway now on this whole chain from about the age of 6 months to the age of 4.5, 5 years of age. So we're trying to connect all the dots. And we think they're all going to be connectable, that this early attention to sounds, the awareness of words, the impact of the language. So you probably know, but maybe not, that being diagnosed with dyslexia is much more frequent in countries in which the orthography, the relationship between the letters and the sounds, is more complex. So for example, in English, where it's fairly complex to relate letters to their sounds because the same sound can be written in many different ways, brings about a much higher diagnosis of dyslexia than in Finland, where there's very little dyslexia, there's a very transparent relationship between the letters and the sounds. So if you have the same brain and you happen to be growing up in Finland as opposed to the United States, trying to map Finnish as opposed to English, you'll have a different level of potential problem with learning to read.
I'm wondering if you can speak to how important parental bonding or familiarity is in language acquisition. For instance, a caregiver or a teacher speaking their mommyese versus a baby who recognizes in their own parent probably is a slightly different level of interaction. Or learning from siblings. So sort of going down the step ladder of what kind of interaction a child has and with whom.
There are a lot of findings in language acquisition literature showing that firstborns who are getting more parental interaction because they're the first have language skills that zoom ahead a little bit faster. And that second-born and third-born children are getting language input from the parents, but less than the first and more from a sib. And so that there are different curves with regard to their acquisition. So hearing a good model of language looks like it's pretty important. We've had a lot of parents in Seattle who are raising kids with nannies who are speaking, about 10 years ago, this was very common, raising children with nannies whose first language was different from English. And parents being afraid of bilingualism, as is common in the United States, telling nannies, don't speak your native language, I only want you to speak English, okay? So a poor model of English to children, which later produced problems in vocabulary growth and grammar and many consultations with parents, who are asking, what's wrong with my child's language? And one of the issues that we identified was having poor input, little input or poor input or both typically, because the nannies were not allowed to speak their native language. Whereas in families in which the nannies were speaking their native language, the kids were thriving with both English and Spanish or whatever the second language. So the model that you hear is important. Doesn't have to be a parent. I think children love their parents' voices. They love to hear them, love to see their parents' faces. But with regard to learning language, a good model is the key. Good model, right from the beginning, and lots of talk in interactive, not just someone once asked me, how many words do I need to speak per day? And I said, it's not a Fitbit for words, it isn't like putting a little toggle on your wrist. It really is this interaction. Now, we don't know how much it takes, but look at the experiments on the Mandarin exposure. 12 sessions, 25 minutes, and the kids were learning like crazy. Now, you have to build a language, so it isn't just that. To grow a language, which is what they're asking me in Madrid, if we want to create perfect bilingual citizens who can speak both languages perfectly well and read and write, what's it going to take? So that's a tall order to prescribe. What do you do every day in the first 3 years to produce these bilingual children? So that's a challenge.
Thank you. It's kind of a continuation of the same question. You were saying that the social interaction when you are speaking that other language at that 3-4 months age, and the pitch of the voice and everything is what made that difference versus watching TV or being in front of a screen. So did you ever try to teach that other language with not such an engaging Mandarin speaker? So someone, but I think relates to the caregiver. If you have a caregiver who is not really that engaging, even if she's speaking another language, but she's very just doing what she has to do and going through the motions, will that impede the learning skill of the child?
No, I know what you're saying. So we've made lots of recordings in homes of children and parents and dinner time conversations. And we can relate the complexity of the vocabulary and the complexity of the grammar to the child's growth in language. So it does matter whether or not you're just going through the routines as opposed to really stimulating language and thought in the child. So children thrive when you're using a diverse vocabulary because their vocabulary is coming from you. So it helps to have a variety of words that you're speaking to children, and the complexity of the grammar and the style of the kinds of things that you talk about. So what's surprising in families in which the education of the parents is very low, they're not talking much to the kids. And when they do talk to the kids, it's more on a directive, do this, do that. Whereas in families in which parents are very educated, their conversations are different in a number of ways. Diversity of vocabulary, complexity of grammar. But they're talking about, we oftentimes measure verbs that have to do with how you feel. So when parents at the dinner table are saying, mental state verbs, we call them. How did you feel about the fact that Susie was mean to you today at school? I mean, complex things that cause the child to think, how did I feel? And how do I put that feeling into words? So in families in which there are real conversations going on, you can see the language grow along in its complexity and in the child's thought processes that go back and forth. Language and thought influence each other. And if a language is to grow and support thinking and vice versa, then it's the language in the home and in the school that's building up that repertoire of the sense that you can express yourself, that your thoughts and feelings can be expressed in words. And I think children come to a kind of, aha, I can write a story that describes how I feel. And that seems like a powerful idea to a child.
I'll admit it, I'm a bad parent.
None of us are perfect.
I put my child in front of the television, I admit it, and I use the baby Einstein videos.
Oh, dear.
So my question is, have you looked at the impact of music on the
Oh.
on brain plasticity
Yeah.
and
Well,
language.
that's a good question. We're and I'm sorry about
Thank
the
God.
baby.
Thank you for saying
I'm sorry
that, by
about
the
the
way.
baby Einstein.
I'll be
Thank-
funding research in the future to a great degree.
Yeah. So we actually think that there is a kind of sensitive period for music too, that exposed to formal musical instruction and musical experience without playing the instrument even under the age of 7 is different than after the age of 7. Now, who knows how many critical periods or sensitive periods exist for different topics, but music is very fascinating. So we're doing 2 sets of experiments at iLabs. The first is a 7-monthers, or 9-monthers, just the same age as the language, are listening to rhythms. They're in social groups with their mothers or fathers, and they're playing drums to a rhythm, okay? They have a wonderful time doing this. And afterwards, after the 12 sessions, we take brain measures in which we look at how the babies are responding to those rhythms, to other rhythms, and to the sounds of foreign languages that use rhythms that they're not used to. And what we see is an extraordinary capacity compared to the control group who came in and played but didn't get the rhythms, extraordinary capacity to lock onto the rhythm and better ability, significantly better, at hearing rhythmic changes in language. Now that's interesting because it means that the brain training that experience not only heightened musical skills, but transferred to a whole new domain, to language skills. So that's a surprise. Now, the second one we're doing is with kids a little bit older, toddlers and kids up to the age of 4. We're giving them an experience with rhythm in social groups, and we're showing that kids who are put in a situation in which they try to synchronize rhythms with another child at between 2 and 4. So no matter what they're doing, whether they're using drums, whether they're even swinging, if they try to swing together in this laboratory experience, that they are more empathic, more empathetic with others, more willing to share, more willing to collaborate, more willing to help. So it's very interesting to imagine that music, these are initial experiments, not published yet, to imagine that music has many, many effects on auditory perception and on synchrony in the brain, and potentially when you act in concert with others, which cultures have done forever in music and dancing and other things that cause us to behave together rhythmically, that we may be encouraging a set of cooperation skills because you have to adjust. You have to be watching the other person, and then you have to work to stay in sync. So isn't that interesting?
That's great for the Diller Quail admissions crew too. Thank you.
Good.
Well, on that note, I'd like to ask you to thank our speaker again. Wonderful, wonderful.